Yeah?
Yes.
Thank you. Do you want to shut the door? No. I mean, I don't mind, but you can. Okay. Right, it was nice to see such a big turnout. It shows what picking a good title means. Not sure the content's as good as the title, but anyway. So we're just discussing, I could probably have picked a title and only about 4 of you came. So. Same content. Okay. I gave a talk last year on languages, programming languages, and how I think they're going to change. And in one sense, this is the other side. Last year it was the how, and this is the why. Okay? So I'm going to talk about big data and machine learning. There's actually lots of MSc courses now on it, so in an hour we're not going to fill a whole MSc in. So it's a nice broad brushstrokes about that. I'm going to try and do 2 things. One is to introduce some of the concepts, and then the second is to show you how, if you're keen, you could go and do a bit of machine learning on a machine like this and get into it. So I think if I can do that, then you might go away. And all the slides I'll put up on Speaker Deck, so you know, so as long as you just get the last one, which is my Speaker Deck account, then you'll be able to find them. Do you distribute slides as well?
Yes.
Okay, well I'll get
together with video.
Okay. Oh yeah. Well, yeah. Don't watch the video. Right. Now, so first of all, I'm going to talk a little bit about big data. So it might be a good idea to know just how big data is. Okay. Because it's not just a lot of data. It's a lot and a lot and a lot of data. So I've been speaking for a few minutes. In the last minute, there were 168 million emails sent in the last minute. There was, there's Google on there somewhere. It's about 700,000 queries to Google. About 350,000 tweets. Sorry. So this is a lot of data. Yeah, Google's at the bottom there. 700,000 search queries to Google. So we're talking about a lot of data. And actually, I was chatting last night in the pub, and I was saying that it strikes me that the thing that's happened in the last 20 years, so which is much more impressive than sending a tin can to the moon and back, is when I came back from Germany in the early 90s to work at Imperial, the UK wasn't on the internet. Okay, Mozilla was the web engine, and Alta Vista was the search engine. Yeah. In 20 years, we've actually got systems that can handle that much data. It is remarkable. And we all take it for granted, don't we, no? You know, nobody actually thinks, you're fiddle with your phone and whatever. Nobody thinks that just what's happened in 20 years, because this was 95, I was working at Imperial, on getting the Janet it was then, onto the internet. So, and actually most of this is started in the last 10 years, when the people decided that they didn't just want to have these big systems, but actually get some data out, which is really annoying, because now if I query anything, I get ads. So I was looking for some hotels for next year in Manhattan, and I get the ads all the time. Do you want to go to Manhattan? We've got some really good deals. So they're all interconnected as well. Okay, so a little bit about big data. Big data, they talk about the V's, and that's volume, in terms of terabytes, although now we talk about petabytes. There's a lot of data coming in, and it's streamed in real time. And of course, it isn't just structured data, it's unstructured. So, so we've had to change the way we handle data. So this is projected volumes. The volumes we were looking at was 2016. Okay. So that's projected volumes. So we're talking about in the next 4 years doubling the amount of data we get, more than doubling. And actually all we was looking at in that first slide really was social media. But all your GP, all your phones, all that data is stored. Sometimes it's stored for processing, sometimes it's stored because of legislation. So I've done some work on connected cars, and the cars have built-in GPSs, which we keep. They also like to see what the wife's doing when she's fiddling around with the internet console, or the kids, I suppose. And then they're providing telemetric data. All that's stored as well. All the transactions to Amazon, all the ones that you do your shopping. So actually, it's an enormous amount of data, and most of it's being processed. And as I say, quite a lot of it is unstructured. So all the maroon here is unstructured text data, and only the bottom bits structured machine data. So to process that data, there was a paper by Google in 2002, 2003, and there was a guy called Doug Cutting, whose child had a little yellow elephant called Hadoop. And he was working for Yahoo at the time, and he wrote a thing on the JVM to process this data. It actually had a quite interesting thing, because the demand for Java programmers was going down until Yahoo came out, and suddenly it went up, and everybody who could program could triple their fees. It was wonderful, really, except for me, because I'm not Java programmer. Okay. Hadoop's now an Apache, as are Spark, and something that's a bit more recent, Storm. And the idea of Hadoop was that you had your data coming in, you sent it to a series of machines, it's called the map phase, you processed those, and then you did something with them and got something useful, which you typically stored on a relational database. It needed its own file system, distributed file system. HDFS stands for Hadoop File System, I think. Okay, and so we've got 3 frameworks for handling big data: Hadoop, Spark, and Storm. All I want to say about them, because I'm not really talking much about these, is that they're all open source, they're all Apache and they're all implemented on the JVM, so in Java. Hadoop, which was the original, is mainly used for batch processing, so we're talking about quite long latencies. Spark is used for batch and also for semi real time, and then Storm is used for streaming data. Right, so I want to talk about data science. Okay, now I'm up to this year, a data science denier, on the grounds that 2 sorts of people in this world: people who believe there's such a thing as data science, and people who don't. However, I'm beginning to think there probably is a thing called data science. I had a look at some MSc and courses, and there's been an absolute explosion this year in people giving an MSc. It's quite easy to do, of course, because all you really do is take modules and bundle them all together, and then you say, here's an MSc. But to give it some academic credibility, rather than just being statistics and a bit of other things, quite a lot of work's now going into what we're talking about tonight: machine learning and big data processing. So, so the data science is a new breed, but data science is relatively confusing. So, this is quite an old slide, which suggested that data science was here at the art here, and you really had the sort of technical knowledge, maths and statistics. You had the hacker, and then you had the person who knew something about the process. And there's bits here. I guess most people now see it more like this. So data science is now all expansive, takes in computer science, takes in maths, and it takes in the domain knowledge. And then the overlaps here, this is traditionally what software, this is really what we're talking about here, and this is the bit in the middle. Unicorn means, since you remember unicorns are a mythological beast. There's nobody, sorry, there's nobody who are unicorns. However, although I don't believe in data science, I've been working in data for a long time, so perhaps there are one or two unicorns around after all. So that's a traditional view now, and we're actually going to be talking a bit about machine learning. Right, so what do you use for programming? Well, MATLAB is a traditional thing for handling data. Octave, people who've used MATLAB. Octave is a free, even slower, but a lot cheaper version of MATLAB. Okay, and I'll put that for you. R, I'm not a great R, but I've got a couple of guys down here who know a lot more about R than I do. Python. Languages on the JVM. Java itself isn't particularly neat to work in, so quite a lot of people now are writing in Scala and Clojure. One of the reasons, because the big data frameworks are on the JVM, it is more convenient to write a jar and throw it on there, and you've got all the Java background scripts available. It doesn't mean that you can't use another language. There's a pretty awful thing called the Hadoop streaming jar. And the idea, and if you want to write Python or anything that isn't, I've got, essentially what it does is it grabs the input and it does something with it and then it comes it onto the output. So it is possible to write other things, but by and large, if you want to do really clever things on a big data cluster, then you tend to want somehow to produce a jar file. SAS is still around, and SPSS, more for statisticians, but people are still selling licenses, especially in the States. And people still do work in Excel. And then, this is the thing, I guess some of you know, I'm involved in the Julia movement over here, and I've written a book. So Julia, I've put at the bottom because it's not used as yet, as are such the others. So, which programming language should we use? Okay. So this is a programming language which is 26 years old. All right. Doesn't have arrays, not native arrays. Okay. And the latest version isn't compatible with the previous version. And in fact, there's more people still use the previous version. Well, the latest version came out in 2008. There's more people using the previous version than the latest version. You guys know which one this is. It's 30 to 50 times slower than binary code, compiled code. And it's the most popular language with data scientists. And actually, at present, it is the best choice for learning, doing some machine learning. So I'm going to show you later how you can get into doing it, and the answer is Python. Right, so Python is by far the best choice to actually get started in machine learning. Okay, so I'll talk a bit about machine learning. machine learning solves problems that, for which we can't use a numerical system on its own. And essentially, you split machine learning into two sorts: supervised learning and unsupervised learning. With supervised learning, what happens is we train the system on a set of data, and we then use the training to provide accurate predictions from new data. With unsupervised learning, all we do is we say, here's a bunch of data, and we ask the system to sort out something from it. So I'm mainly going to talk about supervised machine learning, and there's a lot of categories, but what I want to talk about is regression, which is sort of how much, how many, classification, and then I won't talk about Bayesian, but it's getting more popular. So there's different approaches to doing machine learning. And here's essentially two sorts of problems that come up a lot. So if you have numbers, especially numbers that are written, and you want to decide what's a 1 and what's an 8 and what's a 4 and put them in bins, then you've got to have some sort of machine learning algorithm, and if you've got my handwriting, then it won't always get it right. Okay? So another sort of problem you might have is with emails. Essentially, you want to decide which are spam and which are not spam, and this actually is a big bone of contention, because if you send people's emails into the spam that they want, they get confused. And this one tends to use Bayesian methods, and then this one I'll just talk about a bit later, uses image processing. They're quite good actually on whenever I go in and out of the congestion zone, when I haven't paid, I get fined. So the systems are getting quite good. Obviously, that my number plates aren't in my hand. Well, okay, so what kind of things? I'm going to talk a little bit about classification and what kind of problems. I mean, let's suppose you're going to go and buy a car. Okay, so there's certain things that are going to influence your decision on buying a car. Probably the biggest one will be price. Okay, I mean, you're not going to pay more. Well, you might pay more than before, but so you're not going. So, but there are other things, like whether it's 3 doors, 5 doors, if you've got room for kids, are you going to cart a lot of stuff? So is what kind of car it is. Certain things you probably aren't that bothered about, like the colour. I don't know. So what a machine learning thing tries to do is to say, let's produce some rules that look at all the training data, and let's apply those rules and see how we can, where the cutoff points are which gives us the best fit for the data. And for the fit, we have a thing called the cost function. Now, the cost function is an algorithm that says how close are the predicted values using your algorithm to what you actually got in your training data. So the system will go through and it will look at all the various combinations, say on price, and then little subject on some of the other factors, and it'll produce a tree of various prices. That's quite computing intensive. There are a couple of problems, and one is that if you include attributes like the colour of the car, then those will get taken into the algorithm and they may produce spurious results. So on top of actually doing the classification, it has to look at certain attributes and say, well, I don't want to bother about this. That's called tree pruning. Okay. And the other thing that can happen is that the model might not have enough data either to produce any kind of meaningful answer. So the first one's called overfitting, and the second one's called underfitting.
Martin, when you say not enough data, can you quantify that in any way?
Yeah, well, what you try and do is you try and look at how as you get more and more data, your utility function gets closer, a better, closer to the best fit.
Right.
But what you actually get with an underfit is that it actually can start going down rather than up. So in fact, as you're using more training data, you're actually not getting better results. You could finish up with worse results.
I mean, when you do, for example, online surveys, you typically find that after a few tens of responses, you're getting pretty close to what the final result is going to be.
On an online survey?
Yeah.
Yeah, I
The
wouldn't.
ones that we've done, for example.
Okay.
You might be looking for a sample of 100, 150 responses, but by the time you've got 30, you basically know what the answer is going to be. Because the fit is good enough. Is that the sort of order of magnitude we're talking about, or are we talking about something much, much bigger?
Well, it depends on your survey. I mean,
Yeah,
if you actually had some questions that had irrelevant things, then you might well find that including those will give you answers which are erroneous. So
Right.
you have to look at the survey to say, just as I've said.
But I mean, when we're talking about big data, the question is, do we have to process millions or billions of data items to find a pattern, or can we find it much quicker than that?
Well, it depends on the task. As I say, if you've got a good heuristic, then you would expect the utility function to get closer with the more training data you've got. So typically for, say, this handwritten numbers, you might want to process, say, 100,000 of those. I've got a slide later on the handwritten database. So typically you might have a data set with, say, 100,000, and then you would run that through. This is quite handwritten numbers are quite a tough nut to crack. So you're not talking about enormous amounts if it's converging. Okay, so I'm going to show you a big data, a machine learning program. And this isn't mine, it's this guy called Sebastian Rasker, and he's quite vocal. He's written a book, and later on I'll give you references to the work, what it is. So what do I need to do this? I'm going to do it in Python. So I need a version of Python, and there's one called, guys here, Python people, yeah? No? Not many, okay. Obviously, very often, certainly Linux systems come with Python, but there's
It's sort of schools these days.
Yeah, well, it's on Raspberry Pis and things, but Anaconda is a version of Python that's provided by Continuum. And its advantage, as well as the Python, it comes with all the packages that you might like, all bundled together. So, so you don't have to sort of install the Python and then start getting the packages. So you can install extra ones. It's always good to have an IDE, and the one I'm going to use is a thing called Jupyter, which stands for Julia, Python and R, although you can use other things. Git is a system that you can have for getting information from repositories, and I've got some. And then you need some well-known packages. Python keep telling us that they've got 10,000 packages now, but actually most people only use 20 or 30 packages. And these are all the famous ones. NumPy and SciPy are numeric packages. Pandas is a thing that uses data structures. Matplotlib gets its name from map, and it's plotting. Scikit is very good, and that's probably one of the reasons that you should use Python. And Seaborn also is a data visualization package. So, I'm going to try and do this demo. All right, if I can find the... Okay, now, as I say, I'll give you all... if I get rid of view, I can get rid of that. See a bit more. Okay, there's quite a lot of courses on machine learning, and have you heard of Coursera? Yeah? Okay, well there's a few on them. This other guy's provided on GitHub, he's provided some notebooks that actually solve the same problems that were in the Coursera course. The Coursera course is actually using Matplotlib and Octave. However, he's looked at the same problems and provided this. And I haven't done all these, I've left some of them in, but if we start going down, I hope this works. All right. Okay, so the first thing I want to do is actually use a few of those libraries. So I'm going to just import those libraries. I remember this. Okay, that's all right. And then we need some training data. This particular thing provides us with training data, and this is data on exam, isn't it? So there's two sets of exam scores, and then there's whether based on those that person was eventually admitted or not admitted. Okay, so I can import that. It comes as a comma-separated variable. And then it's always a good idea to have a quick look at a few numbers to make sure it's worked. So this is an exam score for candidate. The first candidate only got 34, but got 78, but didn't get admitted. This person here got 60 and 86 and did get admitted. So this has read this data into a data structure and provided those. It's also a good idea to just have a look at the data. So that's what the data looks like for the whole training data set. So the blue dots are the people who got admitted, and the red crosses are the people who didn't. And actually, as you'd imagine for this particular thing, there's quite a nice boundary here of people. And what we want to say is, given some scores, what's the likelihood that the person will and won't get admitted? So to do this, we use a thing called logistic regression. And for this, we have to define a logistic function here, and the logistic function looks a bit like that. Okay, the idea of this is to actually be able to take a set of numbers from 0 to infinity and compress them into a number that's between 0 and 1, so it becomes a probability. And then we have to say, what's the cost when we start looking at our data? What's our cost function for what we predict as in terms of what we actually get? So we define a cost function here. And if the cost is 0, it means we've got a perfect fit. So any numbers that are bigger means that there's actually a cost. So we use the sigma function here to provide a cost. And it's always a good idea to compute the cost for the first one to see just how far away from the fit it was. The other things we need to do is provide a gradient descent function using our sigmoid here. And then we can apply the cost, and we can predict how accurately we can use our training data to say whether or not somebody will get it. So we get about 89% accuracy from using the training data to say whether somebody will or won't be admitted. The reason we don't get 100% is because what we've really done is a kind of linear regression. So there's these areas around here. There's these areas around here where some of the people here are actually going to be predicted not to get, and some of the people here are going to be predicted to be admitted and not admitted. So we provided this fit. This particular thing also has a more complicated thing, and I'm not going to run through doing this, I've left it done, but the idea of the second data one on this is that there's another set of data which is to do with machine failures, and the idea here is that there's a couple of tests, and the things in the middle here are accepted, but the things on the outside. And for this, we go through a similar process, and in the end, finally get a mean. Now, all that's part of the exercise book, so I'm not going to run through that. So using Python, and you can actually download these, and you can run through, and all the data is available online. Now, if I can get back to... Don't think I meant start, did I? Look at... Yeah, there we go. Okay, so these are some of the URLs that are useful. The notebooks you can get from GitHub. This is where you'll need Git, and you can download these notebooks. The courses are here, and also Sebastian's work, including a book, is down here, and he provides a speaker deck with the slides from a course he gave. So Dave's course at SciPy last year. So if you actually use those, then you will be able to make a start. Now, I just want to talk a little bit about unsupervised learning. So this is deep learning, and Python also has a series of modules that are quite useful. The first one is a thing called Torch. Actually, Torch was written in another language called Lua, but there is a PyTorch, and it's used a lot by Twitter. Now, the idea of machine learning is deep learning. You tend to use neural networks, and I suppose the big thing now is what's called deep neural networks. I'm not quite sure how deep is deep. So traditional neural networks, when we worked them, were only 3 or 4 layers. But I think now you're getting neural networks which should say 20 or 30 layers in depth. You've seen. And one of the problems actually is that whereas you can use a conventional machine to do, although it might be a bit slow, unless you paralyze it, to do machine learning tasks, when you start to do deep learning, you tend to have to use specialized hardware. Now this might be GPUs. We do a lot of work, the company I work with, using CUDA. It's mainly for financial data. However, programming GPUs is not that easy, so there are a lot of libraries that actually try and make it easier. So Theano is a library, and it can actually use GPUs to one of the most popular ones at present is a thing called TensorFlow, which uses the concept of data graphs, and again it uses Caffe is probably on its way out actually, and MXNet's interesting to me because, as well as Python, it's got an API so you can use it with R and with Julia. And AWS are using MXNet. So, however, the other 3 or 4, if you take PyTorch, can all be used with Python. Typical problem is the one we were talking about with handwritten data. So these are the kind of numbers in the data set. The data set's available here on that one, minst, and how you solve it with TensorFlow is here on this URL here. So, so if you actually get into this, you can try running the minst data and solving it. I'm just going to finish up now by talking about Julia, since I'm a devotee. So I run the Julia user group in London, and in a way, Julia was originally seen as a kind of replacement for MATLib, and therefore scientific. However, it's turned out that it's it's very good because it's very quick. It's very good at some of these tasks. What Julia's done, the actual main thing is this Julia Lang, is that they've split the various packages into interrelated groups. This is a snapshot, it's not all the packages, but there is a machine learning package here. I wouldn't suggest that it's anywhere near as good as scikit-learn. So, when will it be? 2 or 3 years, probably. But a lot of work's now going on to try and catch up. The advantage then will be that the actual processing on the machine will be a lot quicker. Julia's about typically 20 times faster than Python, and about 50 or 60 times faster than R. Also, it's very good at parallelization. So it should eventually be a good fit for machine learning. But at present, Python is your best. This is not easy to see, but if you actually, most of these individual community things have their own individual website, and this is the one for Julia ML. So these are some of the various packages that are available. Right. So just to conclude, machine learning approaches are actually computationally very intense. They require a lot. And remember that the growth curve, was doubling the amount of data in the next 4 years. So more and more general purpose and specific hardware is becoming in. And also systems which actually distribute the data and parallelize it. And I actually don't think that Hadoop will be sufficient in the future to cover. And that's it.
Thank you very much.
Yep.
And last point, why not?
What?
Why not Hadoop? What's it missing?
Well, Hadoop's a batch system. There's a lot of work going on, as I say, on semi-real time. The people who are the leaders in this are we call Talend and Cloudera. One of the problems with handling large data is actually moving the data around. Data latency from moving is quite... but if you're doubling the amount of data, then you actually probably need to look at better ways to process it than just using languages on the JVM and the architectures that are available at present. Yeah, that's true.
To an extent, I mean, already Hadoop is largely being used just for data storage, really, and it's feeding into Spark. It's not really being used for processing.
Dave, silly question, you played this up. When you grab data, I mean, I'm a network packet person,
Yep.
so I've been looking at a framework called Grow, and this has potential in that space for parallelisation. Typically, with any learning system, you need some feedback to go and relearn what you know. So that if you've got a structure, I mean, do you fundamentally have, I mean, in my space it would be tell a network tap to run a PCAP file, then go back several years later and say, we had 10 years ago, there would be artifacts. In the future, we'll learn to look for that particular hack. So, in those sorts of scenarios, how do you revisit the learning of what is effectively, to me, your text?
Well, essentially you split your available data into two bits. You've the ones you're actually going to use for your training, and then the ones you're going to use for your back testing.
But does your real live data actually become your test data eventually? That's my thinking.
Well, only if you, I mean, test data you actually have to know the answer, because if it's supervised learning, we're talking about supervised learning, you actually have to...
You go back and you go, well actually, we had this heartbleed vulnerability, we were hacked, and there's no ability to look for it, and we will now continue to actually look for it. And that's part of your learning. So nothing works at that level. Maybe I'll put on this.
Well, I don't know, would you use a Bayesian approach for that then? Because to increase your model?
Isn't the issue there? You're basically saying, oh, I think if we add this extra variable to our algorithm, we'll be able to pick it up in the future. But isn't the whole idea of the machine learning piece that actually you don't necessarily understand the rules?
Well, you don't understand them for deep learning. I mean, if you're using neural nets, with supervised learning, you're providing rules.
But that's the classification, isn't it? If it was a supervised learning, you'd add in as one of your variables the thing that indicated that...
Oh, well, no till tomorrow. So you're continually going back and doing that.
Yeah, so you have to increase your data set of would have thought. But you don't have to specifically say we're going to look for this thing. You just add it in as an extra variable. Don't you?
And then there's a cost.
Yeah.
Thank you.
I wonder if you, neural nets were sort of, I mean, it's obviously a biological analogy people started. So the question now is, how well do you think neural nets do compared to the way real biological systems learn? I mean, obviously, biological systems, you know, they're very compact and so on, but they use small amounts of energy, but they're a bit slow and so on. But I mean, actually, in terms of units, are we actually using, do you think we've got to the right algorithms yet to do as well as biological systems?
I suppose in some things we have. I mean, there's a famous case of playing Go, this DeepMind, which was a British company taken over by Google, and you know, it actually didn't win all the games against. It won 3 or 4 out of 5. But it learned from the game it lost.
Yes, yes. How much hardware did it have to use them?
Well,
we know how much hardware it
a lot,
used.
a lot. Actually, it's interesting because one of the guys who did a lot of work in Julia, originally on the, went to work for Google. Well, I went to work for DeepMind, but they've taken over, and now works over in King's Cross. And they don't allow people, once they work for them, same with Twitter and Facebook, to put things into the public domain.
Yeah, well, quite so.
Well, yeah, but I mean, these are people, you know, who should be supporting open source, shouldn't they? I know they're worried about the intellectual property, but you know, so we actually lose quite good people. They get given a really good job, and then they get poached because they're good, and suddenly you lose a resource.
That's transparency problem with big companies,
Yeah, but you'd hope that perhaps Google and Twitter would have a different approach to.
isn't it? With the internet, I saw everything today. It's about transparency.
Yeah, yeah.
6 or 7 companies that control the world.
Yep.
How much do you think the technology of neural nets has progressed in recent years? Because I was working at an electronics lab in a university 25 years ago, and neural nets are probably the main source of PhDs, and I'd love to see that technology hasn't moved on that much. Am I wrong?
Well, I think it's moved on a lot.
No, it wasn't. Basically what happened was neural networks, deep learning could have happened 20 years ago, but kind of the fad moved away, and there was a couple of problems that didn't get solved, but they would have. There's been quite a few
I think technology's come on a lot though, in the last two or three things. Technology's come a lot, so we get much wider neural nets. And actually, certain people like NVIDIA are now starting to target processing those. So the GPU chips are very, very quick now compared with what they were even 3 or 4 years ago. And they've started providing libraries for DNN that weren't there. Now, it's probably true, like Michael says, that that could have been done if the demand was there. It probably could have been done a few years ago, but not like 20 years ago.
So it was a little bit ahead of time, its time installed. Is that the reason?
Well, I remember looking at some ANDs in the engineering department in Imperial, but I mean, there were nothing as complicated. I don't think the hardware was there to be able to process them, and then, once the hardware and the speed was there, also quite a lot of stuff.
Identical. The concepts were there, they just didn't. Moore's law wasn't far enough.
Yeah. I wonder whether people keep saying Moore's law is going to die quite soon. You know about Moore's law. Originally, Moore said things would double every year, and then he said every 2 years. I think it's about every 20 months, isn't it? Something like that. But there's predictions. It can't go on forever. But, I think the real bottleneck now is storage, and probably SSHDs, chips and things will help there. But it's shifting data around is the latency now rather than processing.
You were talking about scale, and you were saying that 20 level neural nets these days are becoming used. But going back to Tom's question about biological systems with 10 to 11 neurons, presumably there are networks that are very much deeper.
Oh, well, yeah. I mean, a typical neuron connection is about 10,000 connections per cell.
Yeah.
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 So I mean,
But then the question is how many layers do they go to when you can't actually tell just from that number.
no. I mean, there are obviously some neural nets which are totally connected. So every cell in one is connected to the next layer and then the next. There are some that aren't totally connected. They're interconnected either way. So the architectures can be very different, really. But yeah, I mean, you're not looking at 10,000 connections.
Yeah. So it's fair to say that this.
Well, it's fair to say you're trying to mimic the same kinds of things in unsupervised learning.
But it would, I mean,
But
picking up what I think Tom was hinting at, that it's presumably not true that these systems are going to get anywhere near biological levels of learning anytime soon.
Well, I think they do it different way. I don't know. I mean, if you can have a machine that can beat the best Go player in the world 4 times out of 5, and learn in the second game that it lost, and then win the next 3. I mean, you have to say what does. Isn't that? I mean, I don't think it's consciousness.
You're right.
I don't think it's things saying,
narrowly
"Aren't I clever? I've just beaten this guy." But the machine itself has provided some sort of learning process to win.
Yeah, of course.
I have a very naive question. When we talk about like deep learning, is it literally just the number of layers that we can process in a neural network now, or is there something different that's going on there with it?
My understanding is yes, it's actually just the fact that you get much more interconnected deep learning. I don't think there's any real difference between a standard. There's lots of RNNs and ANNs and DNNs. You know, I mean, it's one of those things now. People talk about recurrent neural networks. I'm not going to try that. Pretend I know what those are. So, but I think essentially a deep learning network's just a lot of layers, and typically between 20 and 30 layers rather than just 3 or 4 layers, which would be a conventional neural network.
I first came across the word deep when I read about Deep Blue, which beat Kasparov, didn't it?
Yeah,
I mean, is that similar, or is it?
No, Deep Blue was a machine,
Yeah.
and it actually came from the fact it was IBM, which is Big Blue, aren't they? IBM,
Yeah.
Big Blue.
Yeah.
That's right. So, but it wasn't as far. The point actually when people started doing chess was they looked at strategic algorithms for winning at chess, and they don't anymore. It's just totally if you look 10 moves ahead or whatever, you have pruning. I mean, if you lose your queen, sort of like on the second move, then it's probably not a good idea. Probably forget it. But yeah, so they look. And what used to happen with people like Kasparov was, because they only looked perhaps 4 or 5 moves ahead, if he had a subtle thing that the aha moment that wasn't going to happen for another 7 moves, then the machine didn't see it. You know, and then it was down the wrong. But by exhaustive searching and pruning, I don't think you can now get a grandmaster that can beat a machine. But it hasn't learned anything. I mean, it's just totally algorithmic.
Yeah, don't want to go off topic, but is the reinforced learning something different, better than deep learning? Are you aware of this concept, reinforced learning?
No.
Yeah, that's what DeepMind was. It was a reinforcement learning.
But it's still a neural network,
So
isn't it?
it used the deep learning neural networks to learn what to do, like in terms of to optimize.
Yeah,
But
so
then it used a reinforcement mechanism to come up with a policy.
Yeah.
I understood it was a kind of pruning of the state of the neural network so as to thin down the amount of storage, amount of information that's really required. It's actually trying to get rid of extraneous information somehow, or random information in the net before it continues learning, something like that. Well, I'm just reading the article, it's a descriptive of it.
No questions? I have one question.
Yeah, sure.
Learning from big data, of course, it is challenging and computing consuming task, right? Resources. But what if you need to do a decision based on small data? Like if you want to predict where you want to drill for the oil, you don't do million of drills, right?
No.
It's too many. It's 1, 2, 3, maybe 4 will be the last one.
Probably
So,
a few more than that.
Well, ish.
So, it's just my my brother-in-law
my
says where to
question is,
drill.
what about small data as next big thing? After
Small data. I'm not sure I understand small data as the next big thing. I mean, there's lots of ways of processing small. The problem with big data sets was that, I mean, you could, even with Moore's law, you couldn't, suddenly there was so much data that you couldn't use a conventional relational database or whatever, stick it all on one machine and it's interconnected. So you have to distribute your data and then you have to have different ways to process it. With small data, you can still go back to conventional processing, can't you? You store it in a database and you write some algorithms to...
But
So
to have algorithms which make your right decision.
Right decision. I know when Tony misses it costs £1 million. So yeah, but he still sleeps at night. So.
Okay, I think we can just applaud for a very good presentation. Networking with food and wine, and just to note that at the list I see a couple of ticks for committee, but not too many.